So the idea behind a confidence interval is you're trying to estimate the population mean. So you pick a sample of a certain size. We call it size n, right? And this sample of size n is going to have a certain sample mean. So there are lots of sample means that could occur for the various samples. And these sample means are going to have an approximately normal distribution with the population mean here at the center. So let's say your sample of size n has a particular sample mean. We're going to call it red x bar. What you do, you construct what's called a confidence interval. You go out here to the left, and you go out here to the right. And on the left, you're going to have a number. I'm going to make it a yellow dot. And on the right, you're going to have a number, a yellow dot. And with a certain amount of confidence, you can ensure that that blue population mean is caught in that yellow confidence interval. That's the idea. So here on the left, you have what? X bar minus Z alpha over 2 times sigma over root n. And on the right here, you have X bar plus Z alpha over 2 times sigma over root n. So you're a certain percent, like usually it's what, 90% or 95% or 99% confident that this blue mean is caught in between those two yellow numbers as endpoints. Now, here, this thing that we called the number in the box here, we're going to give that a name. We're going to call that the margin of error. The margin of error right there. I'm going to make it in a purple box. So this is called the margin of error. Margin of error. We give it a name E. E for the margin of error. So the formula for the margin of error is Z alpha over 2 times sigma over root n. It's called the margin of error. Z alpha over 2 times sigma over root n. Now, if you wanted to solve this for n, we'll get n by itself here. What you could do, you could cross multiply here this square root of n with the e. So I'm going to bring the square root of n up here. This is just an algebra trick. I'm going to have what, Z alpha over 2 down here. And sigma stays. But the e, this yellow e right here, this is going to go down underneath where the n was previously. That's just a trick of algebra. Now, n's not quite by itself, right? It has a square root over it, so we're going to square both sides of the equation. So what does the square do to the square root? So the blue square cancels out the red square root, and you're going to have n is equal to C alpha over 2 times sigma over e. All that's going to be squared. This is going to be your formula for calculating what's called the sufficiently large sample size. So n is the sufficiently large sample size. So in other words, how big of a sample do you have to collect so that you're within a certain amount of margin of error? So sufficiently large sample size. So you want to use that formula for finding the sample size that's necessary to estimate something within a certain margin of error. So let's do some problems using that formula. Number 1. Exercise. How large of a sample is necessary to estimate the average height of university basketball players. Within 0.5 inches. So you want a margin of error of 0.5 inches. You want to be correct within 0.5 inches at the 90% confidence level. I spell confidence right? I don't think I did. Spell it right. Confidence level. If the standard deviation for all university basketball players is 1.4 inches. So we're trying to figure out how big of a sample size we need, how large of a sample size we need. So that's going to be n equals z alpha over 2 times sigma divided by e, and all this is going to get squared. So n is what we're looking for. We don't know that. So the things that we are given in this problem, we're given e, the margin of error. What is the margin of error that we want? We want to be within 0.5 inches of being correct. So we want our mean to be within 0.5 inches, so e is 0.5. What's our standard deviation for our population? Standard deviation for our population, sigma. So the standard deviation for all university basketball players is 1.4, right? So it's going to be 1.4. And what is the z alpha over 2, the critical z-score? Well, we're told we want a 90% confidence level here, right? Let's make that in blue, 90% confidence level. So when you want 90% confidence, there's a certain z-score that goes along with that. That's a z-score of, maybe you remember, 1.645. If I plug these numbers into my formula for my sample size that's required, my sufficiently large sample size, I'm going to have, let's see, for z alpha over 2, 1.645, multiplied by sigma, which is 1.4, divide that by 0.5, and then after that square, I'm going to get n is, let's see, so I'm going to plug that in my calculator. 1.645 times 1.4 divided by 0.5. I'm going to get 4.606 approximately. And then I got to square that. So when I square that, let's see, I get about 21.21. Now you always want to round up. If you get a whole number, that's fine. You just leave it as a whole number, but you always round up because you can't take fractions or decimals of samples, right? Samples have to be whole numbers. So you can't take 21.21 basketball players. So if you were to have 21 basketball players, that wouldn't be quite enough. So you have to have at least then 22. So you need a size of 20, sample size of 22. You'd have to randomly select 22 basketball players if you wanted to estimate the actual height of all basketball players within 0.5 inches. Okay, let's do another example. Just for practice, another exercise. How large of a sample is necessary to estimate the average iPad 10 battery life within 5 minutes at the 99% confidence level. If the standard deviation for all iPad 10s battery lives is 23 minutes. So the idea is we want to find how big of a sample we need to take so that we can estimate the average iPad 10 battery life within 5 minutes of the actual value. We want to use a 99% confidence level, and we know that the standard deviation for all iPad 10's battery lives is 23 minutes. We're going to use our formula for sufficiently large sample, n equals, what did it go like? It went, you take the critical z-score, z alpha over 2, times the sample standard deviation, or I'm sorry, the population standard deviation, sigma, divided by the margin of error. You're going to square all that. So what do we have? Do we have the margin of error? Well, we want to be within 5 minutes of the actual value. So 5 is our standard margin of error. Standard deviation. Standard deviation of the population here is 23, right? 23. Now, what's our z alpha over 2, our critical z-score? So notice that we want a 99% confidence level. 99% confidence corresponds to a z-score, a critical z-score of, remember, 2.575. It's one of those 3 big numbers you want to be familiar with. So I'm going to plug these 3 bits of information into my formula. N equals, let's see, I'm going to have 2.575 in place of z alpha over 2. In place of sigma, I'm going to have 23. I'm going to divide that by 5, and then we'll square at the very end. So we want to do the arithmetic in our calculator. So 2.575 times 23 divided by 5. I'm getting, what am I getting? No, let me try it again. It didn't work. 2.575 times 23 divided by 5. Okay, I got 11.845. 11. Then we're going to square that, right? It's going to give us about 140.3, roughly. Now, remember we're taking samples. We're taking a sample. So can we take 140.3 iPads? Can you take 140.3 iPads? No, you can't take parts of iPads, so you have to take whole iPads. 140 wouldn't be enough, so you have to take 141. So always go up if you get a decimal. So 141 would be the minimum number of iPads you would have to collect and test their battery life if you wanted to find the average battery life